underscore token to every post submitted form on your website. And if you forget to add this, you'll get an error message. So those are these automatic protections. So with this kind of specification out of the way, let's talk about how the attack works. Okay? So we need to revisit the semantics of how forms work. This is from a few weeks back, and you'll see a lot of these topics about security and deployment. We're going to be revisiting those same bread and butter topics we covered in the first half of the class. So here's what happens when a user submits a form. The browser first finds all the input elements inside a form, and they have names and values. And the browser creates this thing called a payload of name-value pairs. And then they send it to whatever URL is named in the action attribute of the form. Now, hopefully you're all following this description because you've just finished submitting homework 4, where you had to do all these steps. And here is a last step I wrote. Then your server decides what to do with this information. And when it's deciding what to do with this information, it's got the form data that it was sent. It's got the URL. It's also got the user's cookie. So it knows whether or not the user is logged in and allowed to take certain action. Okay? Now, here's the tricky bit. This part right here, a form submission. You okay? A form submission is an HTTP request, a post request, to the server described in the action attribute. Importantly, it does not matter what website the form itself was on. So, suppose for whatever reason you go to http://my.evil.domain. And you're probably ordering fireworks there. Again, legal fireworks. I want to clarify. You're ordering fireworks there. Maybe not in this state, but in Seattle. Okay? So you're ordering fireworks, and it has a form, but confusingly, that form's action is not the same evil server. That form's action is your bank. And we're assuming here your bank, which it doesn't, has an HTTP method, has an HTTP endpoint that initiates a bank transfer. And you can see here that actually the attacker has pre-filled the correct name and value pairs as hidden inputs. So you as a visitor to this site, you don't actually know what's in these, except that the attacker has put in the amount and the bank address to send it to, and then they've included a button and they've enticed you to click on the button. That's very easy. You put a button that says, please click here to, our server's under heavy load, please click here to proceed. You click the button, unbeknownst to you, clicking the button sends your browser to your bank. It makes a post request. And notably, when it makes a post request to the bank, you're sending your cookies for the bank. Because your browser knows it's making a request to the bank. It includes the cookies for you for the bank. So to the bank, it looks like you as a logged in user have initiated a transfer with certain parameters, except initiating the request is, we call this attacker controlled. I mean, you click the button, but you were enticed into clicking the button. You didn't know what you were doing. And the inputs are also attacker controlled. So this is bad. You do not want the attacker to be making requests on your behalf. Yes?
So does this rely on you having logged into your bank?
That's right.
So if you're doing this in an incognito browser, what would happen?
Well, then you wouldn't be logged in, right? So what's going to happen is you're going to make a post request to the bank by clicking the button. And the post request will say who to transfer it to and how much, which is to the attacker and lots, right? And then the bank is receiving that information plus your code. Now, if you're an incognito tab, the browser says, well, there's a request to transfer, but the user isn't logged in, so they're not logged. And that's fine. But if you are logged in to your bank, then the bank gets a valid cookie. And recall, the only way a server knows who the request came from is via the cookie attached to every single request. So request comes in, it's got a valid cookie. The bank thinks, hey, this person is logged in. Yes?
They have to guess.
Okay, there are 5 big banks in America. Who here has an account at Bank of America? Yeah, I mean, also if one attack succeeds, right? This is the other thing. The attacker is not necessarily trying to get your money. They are happy with anyone's money. So if it's an attack that succeeds 25% of the time, I don't know, 25% of a lot of people's money is still a lot of money. right?
You run multiple, like, you do, multiple. Well, like, when, HTTPs, and you do multiple at the same time.
No, right, so your bank's gonna make one request, but you know, it's first of all, there's only a couple of really big banks, right? JP Morgan Chase, I think, is like twice the size of the next biggest bank in the US. So, first of all, great deal already. Right, second of all, the attacker doesn't have to succeed every time. In security, our goal is to make it impossible for the attacker to succeed, not simply to drive down their probability of success. And by the way, one of the reasons for this is the attacker is a sophisticated actor. So maybe they find out which bank is the biggest in the US, or maybe they go region by region. They look at your IP address. They decide what bank are you most likely at. Maybe they create a variety of attacker websites, right? And those attacker websites are aimed at different segments of the population. One is selling fake Rolex watches. One is selling fake fireworks, right? To go after different kinds of people. Then you figure out where do people shop from these various demographics. So you can't assume that the attacker has a low probability of success. The attacker is working to increase that probability of success.
I think a more likely one is like the attacker's website is trying to pretend to be the bank website, and then it implements something like this.
Also possible, right?
There's a lot of different ways you can do it too. Like wasn't there a thing where Google buys domains similar to Google so that people won't type that in and go to a fake Google and then.
Yep. Yeah, so I mean, and again, when you think about users, don't think about the maximally sophisticated user. Think about, you know, the generalized form of your grandmother. Your specific grandmother might be very capable with computers, but many grandmothers are not. Right? My grandmother is not very sophisticated. So, like, oh, this attack only lets you steal money from old people. Like, well, first of all, that's really bad. Second of all, who do you think has the money, right? Like, so in general, we want to drive the probability of success here to zero. We want a technical capability to totally prevent attacks. And luckily one exists. There is a workaround to this specific vulnerability. So basically, here's just to re-summarize the attack. The attacker convinces the user to submit a form, but on the attacker-controlled website. And probably they describe the form in a misleading way. Right? But that form actually submits to some other service that the user uses because it is a valid post request. And that service receives valid credentials from the user. So this allows the attacker, through the website they control, to take an action on some service they don't control as the user. And by the way, here I've been talking about bank websites. Banks are actually very sophisticated. It turns out that if your literal job is safeguarding money, you become fairly sophisticated about this, but there are lots of levels to this, right? Maybe instead of getting access to your bank account, they get access to your email and then use the forgot your password flow. Now, email services have also gotten fairly sophisticated about this, but what about not the email flow, but the backup to your email flow? There's probably a forgot your password in your email. It might send you a text message. What about your mobile phone carrier's service to get access to text messages, right? So there's a variety of these. You know, a way that an attack chain like this can work is you first somehow get access to the user's last 4 digits of their social security number. A lot of services use that for verification. So this might be as easy as calling, saying you forgot your password. Now you have the last 4 digits, you move up. You go to like Amazon or something. From Amazon, you move up to other accounts. Accounts are typically linked and you learn more and more information about the person whose money you're trying to steal. Eventually, you hopefully have enough information that you can identify yourself to someone who's trusted, maybe the person's email provider, etc. And you know, life is complicated and varied. If you're an email provider, you receive a far from zero, like a definitely positive number of emails every day that says, hey, I'm the executor of the estate of so-and-so. I don't have access to their account because they didn't write it down in their will. However, I'm empowered by the testate court of insert state here to take control of their account to dispose of their affairs. You have a legal responsibility to give it to me. And then you, as you know, a service provider, might not be super well positioned to investigate what the testate court of a state you're not located in, maybe in some district that doesn't really respond to email, thinks about this account, right? So again, the attacker does not necessarily need to directly attack your bank. They might attack a chain of services, gaining more and more proof that they are you or can represent you until eventually getting access to something. We'll talk more about this on Wednesday when we talk about internet crime. Yes?
How does the token prevent this?
Yeah, great, excellent. Thank you for a question that's really a suggestion to me to move on. Okay, so there's a solution to this. Okay, and the solution is actually fairly similar to how cookies work. With cookies, we give your browser a unique identification number that it presents to us to prove it's you. What we will do instead is we will grant an identity to every form on our website. We'll do this with this CSRF token. So what this does is this inserts an extra hidden input element on your site. We can actually look at this. If we go and start the application. Then I'm going to open it up. Here is my login form. This is a form on my website. And if I look into this form in HTML, let me bump the font size quite a bit here and close this. You will see that there's an extra hidden input field at the top with a name of CSRF middleware token and a value of long random string. And the way you should think about this is this long random string and input identifies this HTML form as genuine our server generated forms. The attacker cannot generate a form with a valid CSRF middleware token. Only our server can do so using some tricks of cryptography plus databases. And then when a form request comes in, if it is a post request, traditionally you don't do this for GET requests because you think those are reads, those aren't security essential sensitive anyway. When you get a post request, before performing the action that the user wants you to perform, you will first check whether that action comes from a form that you generated by checking that identity code. So Django, when you write that CSRF token, just expands into the HTML for a single input element. Fairly straightforward implementation. And it will also save that middleware token in your database. That way the server can easily check that it generated that form. And then when a form submission comes in, it'll check, does it have a CSRF middleware token? If not, reject. Is that a valid token? If not, reject. Is it for your user? If not, reject. And if you pass all of those tests, it allows the process to proceed. In Django, this is implemented by something called a middleware, by which I mean it won't even execute your controller if it is rejected. And that's why you get that error message if no CSRF tokens. That's the error message you get when you get a post request. It does not include a CSRF token. You can work around this. You can say CSRF exempt. And in some cases, it might make sense to do that. For example, you might want to allow arbitrary websites on the internet to log users in on your service. Why might you want to do that? For example, you might want to track users across the internet as they view your ads, and those users are not logged in yet. It wouldn't be crazy to make the login form CSRF exempt, since presumably you're already checking the password to verify that this person is correct. But in general, there's not really a good reason to CSRF exempt sites. Very rare that you. So that's the way the protection works. You generate a CSRF token that identifies any form we generate. Any form an attacker will generate will not have a valid token. We'll be able to reject it, and then we'll check that it's a form we generated it for this. We'll know what user it is from the cookie. We know whether or not we generated it from the CSRF token, and the token includes the correct user ID as well. And if those checks succeed, then we proceed. Questions about the CSRF token process?
What happens if the attacker requests that CSRF?
Yeah, great question. So let's do it. Let's do it. Let's attack our website. All right, so I'm going to make a web page on my computer. I'm not going to call it test.html. I already have one of those. Okay, I deleted it. Cool. Hope it wasn't important. All right, let's make a website. Now it's going to contain a form which posts to wherever this wants me to post. So you can see it's localhost /profile/login. Okay, so I'm gonna post to the same exact site, the same exact URL that this form here would post. Of course, here I didn't write the host name, but here I will write the host name because it's going to be on a different. Okay, and then I'm going to include input name equals CSRF middleware token. And I know that name because that's the name that Django always uses. And let's also include a token. So what do you think the token value should be? We got to have some token value. So do you want to propose one?
Still out there already.
Numbers?
Okay, any numbers? All right. Is that good?
Yes.
Cool, cool. Let me bump that actually so people in the back can people in the back see? Excellent. All right. All right. So we made this form and include a CSRF middleware token. And let me actually log in so that we can do something interesting. Let's actually have an interesting attack. Okay, so let's try to change the grade of some submission. All right, so let's here what I want to submit is grade -4, and I want to submit it to /2/grade. So we're going to go to /2/grade, and I'm going to try to change Alice algorithm's grade 100%. 93 isn't good enough. Okay, so I've created this form as the attacker, and we're going to assume that someone has convinced the TA, like for example, me, to go to this website. So here I go. Now here I'm showing you this, but of course in an actual attack, I would likely have made this type hidden. Oh man, harder than you think to spell things correctly. So I wouldn't necessarily see this, and in fact, I might even hide this entry, and so there's just a button that is really convince the user. And if I do this, okay, fine. Okay, so I made that request and it said CSRF verification failed, request aborted. And the reason this request failed is that while I put in a CSRF middleware token, it was not the right one. Now, how can you get a correct one? The way to get a correct one is to visit the website as the user you're trying to pretend to be. But the attacker can't do that, right? To do that, the attacker would need to first log in as the user they're trying to take action. And if they could do that, then like, why are they doing the CSRF? So again, the whole challenge is that an attacker cannot generate a valid CSRF middleware token. Other questions? Yes.
With the CRM,
Yeah.
the tokens,
Yeah.
is it like each instance of a form?
Every single time a form is generated, you generate a new random middleware CSRF token. You save it in the database for this user. You don't want a different user CSRF token to be used because that user might not have the same privileges. Right. So every time you go to a website, on the back end, they're generating a random CSRF middleware token, saving in the database under your user. Once that is used, they are probably throwing that away. Yes.
So if an attacker gained access to a user's account at some point, they were in it and they copied down whatever the CSRF token is, but then they lose access to their account with this.
Yeah, so this is again, the token is generated anew each time.
Okay.
And you are generating it from data only available to the server, not to any particular logged in user.
Okay.
Right. So typically this is a hash of a server provided secret, the user ID, and a random number. And the random number you got to generate in a cryptographically secure way. I'm actually skipping the discussion of sort of the details of the cryptography, precisely because I don't want to teach you how to implement it, because I'm not going to tell you everything you need to do to implement it correctly, and I'd rather you just not know. You can take like the security class, which will tell you how to do it right, with all of them.
Yeah, Professor Nag did a great job teaching out. I'm in it right now. I'm just talking about this right now.
Oh, awesome. Well, yeah, so you should have been taking the class all along. Okay, so we've looked a little bit at the CSRF tokens. I want to push on a little bit, just to generalize a little bit, what we've done is we've applied the same trick we used in cookies. We've created server granted identities, but not for users, for individual forms that we generate. Every single form is assigned a CSRF token. It stores that token in its source code. And then the database has a list of all the valid tokens for all the valid forms and which users are supposed to submit which forms. And so every form submission can be on it. So this is an example of how we can use the same technique of cookies, more broadly, this technique of server granted identities, and reuse it. And by the way, this same technique, we're going to use it in a lot of other parts of an application might make use of. So if you have like a forget your password link, it'll work in much the same way. Now there, some kind of random password or some kind of random token will be inserted typically into the reset your password URL. Presumably you've seen that. So that link isn't like /reset/ your username, it's /reset/ random string. That random string is connected to which user requested that password reset. So again, we're using server granted identities there. We'll also use server granted identities in a variety of other ways. So if you have multiple services interacting, often those will be signed by services. Okay, cool. So that's classic bug number 1, CSRF tokens. Let's move on to a second classic bug. Someone say something? Yeah, great. Yeah, so let's talk about injection attacks. This is another broad class of attacks. Classic, you see it all the time. So this is a category of attacks that includes SQL injection, cross-site scripting, which you can call JavaScript injection, command line injection, and a variety of other injection style attacks. So what the specification of the attack is like this. This is an attack that allows the attacker to modify the code your application executes. Now, understandably, that's pretty bad because your application probably has a lot of privileges to your application, right? The code of your application can probably access anywhere in your database. It can probably execute and access any information about the current user or other users. And it can potentially, just like delete the database to mess with you or do some other kind of attack. And, the delete your database to mess with you, that might not directly lead to gain for the attacker, but it may, for example, bring your service down for a day until you restore the attacker. And that might be valuable for the attacker in a variety of ways. Maybe if your service is down, some other security protections for some other service won't work. Or maybe it'll distract from some different attack that the attacker is doing at the same time. Or maybe the attacker bought a bunch of shorts on your company and they're just hoping the stock market goes down as part of your attack. You joke, but people are sitting in federal prison right now for attacks of a similar kind. So again, we really don't want the attackers to run code as our application because our application is very privileged. And importantly, the code can run as another user or even as the application as a whole. And it allows attackers to circumvent all the normal authorization. So it's really bad. And there's a defense against this. This is called data escaping. And it's something that Django automatically applies in a whole lot of places. That said, in a complicated application, you will almost certainly create new and fascinating kinds of injection attacks. So this is a case where the most common kinds of injection attacks, Django protects you from them. But sometimes there are reasons to circumvent those protections. And also, in a complicated application, you're probably also going to have types of injection attacks that Django doesn't protect. So let's take a look. So here's what an injection attack is. It's when you generate a string, you intend that string to contain data, but it is interpreted as if it contains code. And the variations of this attack depend on what kind of code it's interpreted as. So let me look at an example, and here I've chosen an example that's not sort of the most standard one, so it's hopefully something you haven't seen. Here's something that you might have in your application. You might have an application where people can upload a video into your service. Think TikTok, right? And when someone uploads a video, you'll probably want to convert it to a different video format. One maybe you downsample it for slower mobile devices or something. And a great thing that you might think of doing is using the FFmpeg tool, which is a free video converter, fairly efficient, state-of-the-art. And this is how you might use it. You might try to video convert a file by constructing. You okay?
Yes, sir.
Okay. You might try to do the video conversion by constructing a shell command. So this is a super reasonable command, ffmpeg, input file, your file, output file, something.mp4. This will cause ffmpeg to convert whatever the user uploaded to an mp4 file. And this will work, but I put this in code for shell in blue, because I want you to think about what would happen if you didn't have that. You would still output ffmpeg-i, your file name, output.mp4. But if the file name is, for whatever reason, specially constructed, for example, like this, the shell will not necessarily interpret it as a single file name. For example, if this is the file name, the shell will see three commands. ffmpeg-i, which will cause ffmpeg to print a help message about how you should use the -i flag. Then the command rm-rf/, which will delete every file on your computer. And then once it's done with that, it'll see the command ls output.mp4, which will attempt to print statistics about the output.mp4 file, which at this point is probably deleted. So this is a valid sequence of three commands, not the one command you intended, and it results in every file on your server being deleted. Now, every file on your server being deleted is not actually the worst case. The worst case, right, is that they actually run a small Python command that goes into your database, changes the attacker's user to a super user account, and then otherwise silently exits. And in that case, you probably have no trace that this happened. And you have no clear way to find out like what bad occurred, except that the attacker is now a super user and can probably do all sorts of bad stuff. So this is a case. Now to run through my typology of why this works. You have a string, the input to this run function. That string is intended to contain some data, the file name, which is attacker controlled. But instead, that string is misinterpreted as containing code. So here, if the file name is this is interpreted not as data, but as a sequence of additional commands for the computer to execute. And the solution here is that typically, basically all programming languages have a way of encoding the special characters so that they don't mean code, they mean data. Simple example of this that you've seen is that if you write a string literal in a language, you can put a \n into it. That doesn't explicitly mean backslash, the letter backslash and the letter n. That means a new line. And the reason for that is because you probably can't put a literal new line in the string in that way. Same deal here. So for example, in the shell, you can use single quotes to escape a file name. So if you write the encode for shell function the right way, you'll actually execute this command, which will correctly be interpreted as having a single operand for the input file, which is just this fucking name. And I should say, you know, in this command line injection, not every program has a command line of certain kinds, but almost every web app generates HTML. And a really similar problem can occur there. So for example, if you're generating HTML, you might want to greet the user. But what if the user's name itself is some HTML code? If you don't escape that, then the browser might interpret that as part of the web page. It might interpret that as part of the web page. For example, here I have a name followed by a form, but the attacker's name, for whatever reason, because they're evil, I guess, makes the form actually submit to their website. In HTML, if you've got nested forms, the inner one isn't. So in this case, the attacker can make the user think they're taking an action on the user site, but actually send that data to the attacker. So maybe if that data is private, maybe if it contains a CSRF token, for example, then the attacker can get access to it. So this is HTML injection, and there was a variety of similar cases. So this was, people today probably don't read XKCD, but back in the olden days, this was a webcomic people liked. And it's pointing out the same thing. So the woman gets a call from her school that says, did you really name your son Robert, single quote, close paren, semicolon, drop table students, semicolon, dash, dash. And the implication, of course, is that they have this as a snippet of SQL code, a fragment of SQL code. And the implication is that somewhere, the application that's processing their son's name constructs a string by concatenating their name to some SQL code. And then this close quote, close paren, semicolon, ends whatever previous query was being executed and executes a second query called drop table students. And then there's dash dash at the end that starts a comment so that anything else left off in the command that's just ignored. And so presumably this would first execute the query it was supposed to execute, and then it would delete the table containing all the student data, which is why, of course, the school is called. And again, I want to emphasize, drop table is maybe a fun thing to do, but it is equally possible to modify the database in some essential. Yes.
Yeah, the TSA had a thing where some researcher would do that exact like closing thing and it logged them in as administrators, so they could like make themselves
Yeah.
pre-checked and like.
Now I'm telling you about these mistakes because they're all over the place. And actually I should know, on Wednesday, we will talk about computer crime and the laws around it. So until that lecture, please don't go pen testing your favorite websites by trying to execute some of these commands, okay? We'll talk how many years you'll get in federal prison for that on Wednesday. And until we have that discussion, you can't really make the cost benefit calculation. Okay, but so these are 3 examples. We have SQL injection here, we have HTML injection right here, we have CLI injection right here. And in each of these cases, the solution is the same. You want to ensure that whatever language you are constructing code in, use the appropriate escaping mechanism to ensure that the data is interpreted as data. So in code for shell here, and code for HTML here, and presumably in code for SQL here. And these would be functions you have. So let me pause here for questions about how the attack works, and then we'll talk about mitigations. And I saw there were hands in the back, so now's a good time. Yeah.
I was just gonna clarify, so this is something that the TSR prevents?
No, different attack. Different attack. This is a valid submission from a validly logged in user whose name they truly pretend is this string. And the problem is you're not executing the SQL queries you thought you were executing, or you're not generating the HTML you thought you were generating, or you're not executing the CLI command you thought you were executing. And in fact, the attacker gets to control what shell commands, HTML or SQL is being executed, and the attacker has different ideas from you on what those should be.
So Django sanitizes all of your inputs for you.
Yeah, we'll talk about Django's protections for this in a second. Other questions? Yes.
Isn't the HTML example particularly terrifying though?
They're all terrifying, man.
Well, at least with the other ones, like a hacker would need to like try a bunch of websites and like, maybe they have a 0.01 chance that one of the websites has that vulnerability. Well, maybe higher, whatever the number doesn't matter.
Yeah, but
in the case of HTML.
Okay, I suppose I should clarify. When someone bad tries something on your website, you won't find out. Like you don't get like an alert on your phone being like hackers. And there's a good reason for this, okay? By default, you probably didn't set up this login. But if you did, you'd get a notification of this roughly every second. So, I host some websites online. So attackers are constantly trying evil stuff on your website. I guess that's the point. So, for example, this is the server on the internet somewhere that serves my personal website and also the website for my textbook. So let's just bar log nginx access.log. Let's just look at a log of what requests people are making. And you can see that these requests here, the timestamp is right here. These cover the last couple of minutes. Probably lecture started around here. So there's a couple of requests, I'm not super popular, okay? So we got a couple of requests per minute. And a lot of these are normal, like this one here, /blog/oh on Herbie, that's a blog post I wrote, right? Get / that's, that's the main page of the website. But this right here, /data/admin/ allow url.txt, that's not a page that exists on my website. That's just someone trying something. Real website, real website, real website, real website, real website, fake website. I don't even have PHP on my website. This is just someone trying something. And in particular, XML RPC is typically the endpoint at which you can do remote commands like administrative commands. So presumably they would go here and then they would try to log in as maybe admin:admin and then see what commands they can send to my server. Similarly, this is an attack. Okay, so if you go back, you'll see a number of these. If you look at my website statistics, you'll see that we get a couple hundred of these per day. And you'll get the same thing if you look at SSH logs, people trying to log in. You'll, various other services that you might provide, like people try to log into your database and access that point, et cetera. So on the open internet, man, people are trying attacks on your computer, on your server, just constantly.
Yeah.
And there's no way to stop them. Yeah, it's just like, it'd be like if you lived somewhere and just like every couple of minutes, someone would like jangle your doorknob just to make sure you locked in. If you did that, that'd be if that was your real life, you would consider that an insanely high crime neighborhood, like way more so than anywhere that actually exists on any country on earth. But on the internet, that's just life all the time. So, yeah, I mean, people are just trying this attack all the time, as they are trying to log in with invalid credentials or check if you have an old version of WordPress that's vulnerable to some kind of attack, etc. So yeah. All of these attacks are terrifying precisely because people are trying them all. They're doing it because they make money by stealing people's money, right? There's an organized crime syndicate, sometimes state that are doing this. Okay, so generalizing a bit, you're frequently generating code in your application. Code in a broad sense. You're generating SQL queries, that's code executed by the database, CLI commands, that's code executed by your shell. HTML, that's code executed by the user's browser. JavaScript, JSON, URLs, etc. Loads of different text in this space. And anytime you're generating code, you have to think about escaping data so it's not misinterpreted as code. So the way you do this is, on a first level, the first sort of cut is you become familiar with the language that you are executing. Most languages have some way of escaping raw data so it's not misinterpreted as code. So for example, in HTML, I taught you the HTML entities. And those allow you to generate less than signs and greater than signs that won't be interpreted as HTML elements. So then you can perform an escaping pass. You can look for all less than signs, ampersands, and greater than signs, and replace them with the appropriate entity. And if you do that, the browser will now not misinterpret data as code. Similarly, in SQL, different SQL databases work differently. SQL is a mess, but there's usually some kind of string escape. There's usually some kind of command escape or quote escape as well. In the shell, there's typically escapes as well, like \single quote, et cetera, et cetera. And this can get challenging. Sometimes you have nested languages, like you have JavaScript code that's embedded in HTML code. This was an injection bug I found in Dropbox while I was there. And then you have to escape it twice. You have to first escape it as JavaScript code and then as the embedded HTML code. You want HTML to treat it as data. And then when JavaScript executes it, you want JavaScript to treat it as data as well. Yes?
If you have like a really weird username or password by using special characters like this?
Yeah, I mean, so like one great thing about Django is that let's go back to the actual application and let's go to and I'm going to go to the admin page and I'm going to create a user. Let's try it. See, okay, so Django will prevent me, but this is okay. Django will prevent me from making such a user, but there's no real reason that you should. So the database should prevent an attack from this. And I'll generally say that preventing certain characters from showing up in your database or in your users is not a good approach to this problem. First of all, databases change and what special characters mean changes over time. You don't want to be in the bad situation where like ampersand used to be okay, but now it's not, it means something. And second of all, there's this broader problem that the language's rules are often complicated and contextual. So for example, I didn't list double quote here, but if you're putting user data inside an HTML attribute, you probably should escape it. And what about raw bytes, just like, I don't know, the byte like, 173. That's not meaningful in HTML, but maybe under certain encodings, it's interpreted as something meaningful. So typically preventing input data, not a good approach. You want to ensure that it's safe. Yes.
Kind of funny, but evil is not a website, but evilevil.com is.
Yeah, that makes sense. That makes sense. There's real people out there. That's just life. Okay, so let's talk about how Django helps you out with this. Okay. The great thing is that Django has wrappers around a lot of the cases where you might want to construct code. So in Django, you typically don't write Python code that outputs HTML. you instead execute a Django template. And in a Django template, anytime you do those double curly braces, it automatically performs HTML escaping. So if you have, let's just go in here. Let's go into our test application, the horrible one. And we can go into templates, and I believe there's one called hello. And you can see that right here. Yeah, there's this favorite, one of these variables I think is attacker controlled. Let's check this. Okay, so here I changed this favorite student variable to come from attacker controlled data, which is the that text URL. So let's launch our test application. Yeah, if you can't see in the back, let me know. I probably can't, but this probably can. Bug left over from the previous lecture. Okay. So if we go to localhost/hello/me, you will see the application declare that I am my own favorite student. Excellent. But if I change this to be form, and note that I've added those angle brackets into the URL, you will see that Django totally successfully outputs literal angle brackets. The browser doesn't interpret that as a form, and the reason it doesn't is because if you open the source code to this website and you look at it, you will see that this favorite student bit here is encoded using those less than and greater than schemes. So Django has automatically provided that escape for HTML functionality, avoided an injection attack in this instance. And Django is likewise going to do this if you use the query API instead of writing raw SQL. So again, if you perform SQL queries, you're going to insert some data, like you're going to look for, student.objects.filter name equals ... Django will automatically make sure to escape that ... according to the rules of SQL escaping. Yes.
So I was just gonna say, doesn't did Django by default it by default doesn't allow you to like just do raw HTML, right?
That's correct. So again, Django prefers you to use these safe APIs, and these APIs automatically perform the escape. That's the good news. That said, there are going to be cases where you want to circumvent these. In your third homework assignment, you probably saw this pipe safe filter. It's called safe because you're here asserting that the data you're printing is safe for some reason. In your grades application, what was intended to be safe was the description of an assignment. And the reason it's safe is because the only person who's allowed to edit the description of the assignment is the professor, who probably does not intend to hack their own website. However, more broadly, anytime you use pipe safe like this to output raw HTML, you've got to be really careful. You have to think, who could this HTML have come from? Could it come from an attacker? If so, they'll probably be able to do something evil by injecting code into my application, so don't let it. And similarly, there are cases where you'll want to use something like .raw. So this is an API in Django that allows you to issue raw SQL queries. And sometimes you might want to do this because you might have a really performance sensitive part of your application where it's important that you generate exactly the SQL query that will execute the fastest. You have, professional DBA, and they figured out how to execute this particular query as efficiently as possible. And you want to make sure to execute exactly that. In that case, you might use .raw, but then the burden is on you to prevent these injection attacks by making sure to escape everything correctly. And there's actually a great thing that Django provides these. First of all, it's really easy to forget to escape something. That's just like you're writing code fast, you got users who really want features, or like a boss who desperately needs something done quick, and you might accidentally forget to escape something. But the other reason it's really good this is built into Django is because you probably don't know the precise lexical details of how every programming language you're interacting with works. So for example, does anyone here believe they know the exact set of letters that are allowed to follow a backslash in Python? as a backslash escape. Let's do a quick poll. Who thinks \n is a valid escape in Python? Yes, correct. That means new line. Okay. Who believes that \q is a valid escape in Python? You wanna state your case?
I just think it will be, I have no idea.
It is, in fact, it stands for qualified name. It's a Unicode thing. What about \v?
Like as a dog?
V, like Velociraptor.
Yeah.
Anyone? Stands for vertical tab. Yeah, so Python's a language you've been using in this class for a while, but these are still details you've had no reason to learn. Similarly, there's a good chance you don't know which databases use \double quote and which databases use 2 double quotes in a row. Yeah, some databases do that. Or which characters exactly terminate a string in JavaScript. And in Python, at Dropbox, we had a bug precisely due to this. So you typically don't want to write your own escaping. It's easy to say, oh, I'll just escape the most important characters, less than sign, greater than sign, ampersand in HTML. But then you have to think, what other parts of the HTML syntax am I not thinking of? That in some kind of weird circumstance end up being semantic meaning. So typically, don't write your own escaping logic. You'll want to use a widely used library. Widely used is important because this means someone with training and expertise has probably looked into whether or not it does the right thing. And you want to use that for your escaping logic. Luckily, Django comes with a good HTML escaper, comes with a good SQL escaper. But if you're doing something else, you're shelling out to like the command line, for example, or interacting with another service, you're outputting JSON code, etc. You're going to want to use an escaping library that's going to work for you. Yes.
So you said there's a lot of different variations of injection attack. Is there anything?
Basically, variations on just what language you are generating. There's a good chance that at some point in your life, if you write web applications, you'll need to generate a PDF. Then you will need to learn what characters or bytes are semantically meaningful in a PDF and could be used for a PDF injection attack. And there's no reason for you to know this now. I mean, if you do, congrats, talk to me after class, but I'll find out why. But you'll have to generate JPEGs, you'll have to generate XML files, you'll need to generate JSON files, you'll need to generate PDFs, you'll need to generate all kinds of other file formats, and all of them typically have some distinction between code and data that you'll need to be cognizant. Okay, so this is classic attack number 2. Let's talk about classic attack number 3. This is an open redirect. Okay, and this is actually something that you will have to take manual action to prevent in homework problem. So listen up. Open redirects are a kind of phishing attack. When we say phishing attack, we mean a specific thing. We mean the user goes to an attacker's website, but is confused into thinking that it's, say, their bank website or their email website or something of the sort. Think about people who type the word Facebook into their browser address bar and end up on the Google search results for Facebook. Now imagine that you pay a whole lot of money to be the first result for Facebook on Google. Now, that would be a gargantuan sum of money to do this for attackers in general. But what if, for example, you want to target one particular user? Possibly you can add target to that one particular user and outbid what Facebook is willing to spend to target a specific user. And then they end up on your website, on the attacker's website, instead of facebook.com. But you can make your page look like the real Facebook website. It'll have the same logo, the same style. It'll have the same username and password box. And then the user thinks that they're typing in their Facebook username and password. But that data is sent to the attacker, not to Facebook. And then the attacker logs into the actual Facebook account on their own time and does whatever evil stuff. And it's really hard to fix this. As an employee of the state, we get emails once a month that pretend to be phishing websites. And then if we click on the link, we get sent to mandatory training. I don't think the training does anything because they keep running it.
Yeah, they do send to students as well, actually.
Oh, great. Okay, so you've seen it.
Yeah.
And in fact, users are distracted very often. They are doing other stuff. They're using your application. They're in a hurry. they have a deadline or some other thing. Also, a lot of people just send emails that look pretty darn suspicious. For example, there's important accounting task that I have to do as a professor to make sure, that the money is spent in accordance to the rules with which it's in our budget. And those emails change every 3 months. So I got that email and it had a different design from what it did before. My assumption is they changed the damn design again. Because they do this all the time. And I don't know why they changed the design of the email, but they do. And so if I got one that looked weird, I wouldn't think anything. It's pretty hard to make it difficult to replicate the real website. So phishing, really hard to fix. Your users will end up on a site that looks exactly like your website. And we try to educate users to do stuff like, for example, check whether the URL is what you expect. So for example, if I go to, you can see that my browser, for example, prints just the host name in the top right corner. So if I went to evil.com or facebook.com.evil.com, it would actually print evil.com there. So hopefully the user would not be tricked into thinking they were logging into actual Facebook. But a lot of effort has been put into educating the user to check the URLs. Another thing is if the password autocomplete doesn't show up, maybe this is another case where the user might get suspicious. The password autocomplete is based on your actual host name, and you don't have any password saved for evil.com. And of course, don't click on links and emails, but that's a lost cause. People do that all the time. So open redirects are an attack specifically on this first check. Users have the habit when they are logging into a website to check the URL, especially if they followed it from a link in their email or something. And an open redirect lets you circumvent this simple check. It involves that redirect URL that's part of a login. You remember that last week we talked about implementing user login. And we said that after the user logged in, you typically take a get parameter, which contains a redirect URL, and you redirect the user to that URL. Well, that means that URL that the user is redirected to, that can just be part of a link that the attacker specifies. So here's how the attack works. The user clicks on a link to the email in an email. It sends them to the real facebook.com with a redirect URL pointing to evil.evil. The user successfully logs into facebook.com by typing in their username and password. Because the login is successful, they're logged into Facebook and sent to the attacker's website. The attacker's website conveniently looks exactly like the Facebook login form, plus the error message, your username and password did not match. The user has already performed the check. They know they're on facebook.com, so they don't think to check the URL again. They type their username and password in once again. They're not suspicious that the autocomplete didn't pop up because they figure since they failed to log in the first time, they shouldn't trust the autocomplete. And now they log in. When they log into the evil attacker's website, the evil attacker saves your username and password, sends you back to the real facebook.com, and the user is none the wiser. So in this process, we have first sent the attacker to a URL of our choosing, but we chose that URL to be the real facebook.com. But then we tricked facebook.com to redirecting the user to our website, where we misled them into entering their username and password. We circumvented this habit users have of checking the URL because they already checked the URL the first time when they log in successfully, and we got their username and password for it. I guess this doesn't sound terrifying because none of you use Facebook, but if it's like your email provider, your bank website, or something similar. So questions about the attack here. It's somewhat complicated, but we're circumventing an existing protection, which is users' habits of checking the URL. Yes?
How does the hacker get Facebook to redirect you to?
Ah, great point. Well, let's go to our very own login form. We call this? Yeah. So here is our application, the bad one that we've been developing throughout the class. And here, I believe, so just checking the code, you can see that upon a successful login, we redirect to the next URL, which we get from the get parameters in the URL under the key next. So here, I'm just going to go to login.com !next equals https://google.com. And I hope pen is the correct login. So I'm going to log in. Huh? Okay. Let me see what happened next. Next equals. I probably need to URL encode this. 1 second. We'll go to code URI component // Google. All right, so this is the string I'm going to stick into. Login, question mark, next equals. I'll just copy that. HTTP %3a %2f %2f. So now I've gone to this URL. Because of how our redirect URL works, I have constructed a hidden input. Next parameter is http // That's the next value my server will see when I successfully log in, and my server will successfully redirect me to google.com. Of course, with google.com, that's not super scary, but if it was another page pretending to be an username and password did not match page for your website, you'd be pretty tempted to immediately log in once. So that's how we trick yourself. Questions about the attack? Yes.
What was the URI?
Oh, the first time I tried this, it didn't work because I put a / in this like get parameter thing, and you're not supposed to do that. So then I fixed it to use these % escapes, and that makes it part of the data. This again escaping.
So then if the person that was like,
The attacker would of course do this ahead.
Is there nothing we can do to stop them from specifying the next?
It's a great question. You're just trying to move the lecture along. You got someone to be. So here's how we prevent this. In Django, there's a function called URL has allowed host and scheme. Why is it this long? I do not know why it is this long.
Wonder what it does.
It checks, however, whether the URL has an allowed host and scheme for redirection. So if it returns true, it's valid to redirect to that site. If it returns false, do not redirect to that website. So I can show you how that looks in code. Right here is our redirect call, and right above it, I'm going to do if URL has allowed host and scheme. And the arguments to this are the URL and the word none. Django's a little configurable, so you can specify which additional websites are allowed. None says no other websites. So if that's true, then perform the redirect. Otherwise, I'm just going to append an extra error message to my site. I'm going to say, someone is trying to hack you. Close the tab and hide under a ticket. Again, don't actually write this error message, but you get the idea. Here, you would, instead of performing the redirect, just either inform the user, or another thing that you might do right here is you might return a redirect to the main page of your website, which is a listing. Yes.
Does that mean you have to define the valid URLs that can be used, or is that just used?
Django will, so if you pass none right here, then what this method checks is it must be yours. So that's what it does.
So I guess we're taking like a list of valid.
Yeah, exactly. You can provide it a list of other valid listings. If for whatever reason you have like a, if like Facebook.com and Instagram.com are allowed to redirect to each other because they share a common login system, then you might want to do something like that. So again, let's go back and try to perform our attack once again. Oh yes, of course I have to import this. I wonder where we import it from. From Django.http import URL as valid host and scheme. No. All right. But now where we import this from? Oh, actually, I think I said in home request.
Utils HTTP.
There we go. .utils.http. Okay. That was close. All right. Nope. has allowed hosting scheme. There we go. All right. So reconfirm form submission. Okay. There, the CSR verification failed because I was submitting that form for a second time. I refreshed the post request to go through, and I already used that. But let's try one more time. Here it is now redirected to the / URL. Now that URL doesn't exist, but it went through this else clause where it redirected this. So I didn't end up redirected. So anytime that you perform a redirect, you need to look at where that URL came from. And if the URL could possibly come from the attacker, you need to make sure that you perform this URL has allowed hosting scheme functionality. Okay. Moving along, we've got 10 more minutes. Yeah, okay, so basically that's the situation. I have not every framework will have something like this, but the test is actually pretty easy. You check that the URL starts with a /, but does not start with a /. And that's enough to ensure that it's a URL on your specific website. All that Django's URL has allowed hosting scheme does is it performs a few extra configuration options like in that Facebook to Instagram scenario. Okay, so questions about preventing this attack. Yes.
Why does / I didn't understand that last line.
Oh, if your URL starts with a single / and doesn't start with a /, it's a URL like /profile, and that refers to something on your website. And since it's on your website, it's definitely not on the attacker's website, so it's safe for you. Starting with a / is this obscure thing called scheme independent URLs, and those would allow the attacker to go to another website. So this is the check. Single /, not /. If you want something more complicated, like multiple allowed host names, there you got to do your research. Yes.
So I'm still a little confused about the redirect attack example of the user goes to the actual login page, but gets redirected by it.
Okay. Let's walk that through because it's important to understand. Okay. So the attack works something like this. I'm going to write a little email. Okay, I'm going to email you. I'm not going to actually email, but the email is going to say something like this. Hello, we have detected that your Facebook account, let's actually say your Facebook account may have been compromised.
Leave the typos.
Okay, yeah, everyone knows that you're supposed to leave the typos because then you're filtering to users who don't read very carefully. Please log in once again at the following website. Yeah, leave the typos. Okay, and the attack is gonna the URL is gonna be full faith and honesty facebook.com/login ? After the question mark, it will say next equals, and here I mostly spelled out the URL, but the attacker wouldn't do that. The attack would say, percent. I guess it's like a 5A, percent 5C. You just get a lot of these percent escapes. And no user is going to look at that and think the URL is unsafe. Even a very careful user will investigate this URL and say that is actually for real a facebook.com URL. So then they end up on a website like this. And they check once again in the corner and they see that for sure, for real, it is facebook.com. And by the way, their browser autocomplete also checks the URL and also allows them to log in. So the user will totally successfully fill in a form like this. And when they click login, they're going to be redirected to the attacker's website. Now, what is the attacker's website? The attacker performs the following action. Okay, they do view page source, copy. And then over here, they're going to do, let's make our evil.html. And they're going to copy and paste the same exact information. And they're going to make it redirect to the same exact page, that literally identical HTML. Except, of course, it's on the attacker's website. So they're going to start up a server serving that URL. I can actually actually do that. Okay, so now I have the real, I mean, it's not Facebook, but this is our stand-in for Facebook.com, the real thing. And we also have localhost 8001, an identical looking website. The same in every way, and maybe the attacker will even go in and modify it and say, output invalid username and password. Please try again. So now this looks exactly like our login page would look if you had typed in the wrong password. So what the attacker will do, they will cause the user to go to http://localhost 8001/people.html, and they'll stick this in the redirect portion of the URL. So they will go to login next equals this. Autocomplete works. It's for the correct website. Everyone is happy. User performs all their checks. It is the real website they were intending to go to. The URL really is correct. And this next URL is made totally unreadable by escaping every character. Then the user clicks login. Oh, yeah, well, we added the protection. Let me remove the protection first. Yeah, we've successfully prevented that, but you want a demonstration of what had happened. Let's go back to the way it was. So user logs in and is redirected, man, totally seamlessly, but this is an attacker controlled website. The user probably does not recheck the URL, make sure, hey, that's the wrong port number or whatever. Because like the user already knows they're on Facebook, they already know they just typed in the password. It's totally reasonable to them that the password is incorrect. So they're like, oh man, okay, let me try again. But now this is an attacker controlled form. It'll submit to the attacker's website, which will just save my username and password, redirect me back to Facebook where I'm correctly logged in.
So that redirect is happening because of the next.
Exactly, exactly. And we talk this is a completely standard part of all login forms. It's a functionality that Django ships with by default, handling these login forms, these login redirects. And we looked last week on Wednesday, like GitHub, for example, implements that same function. Yes.
And so the main way to control that next part of the URL is through the name.
Sure, or any other way that you could send that, any other way that you can convince a user to click on a link. And somehow convince the user that they should expect to be on Facebook and should expect to log in. Yes.
That seems prone to error though. Why do we use the URL has allowed host and scheme, the longest function I've ever seen in my life? And why don't we instead just instead of redirect, it automatically checks?
That's a good question. That's something Django could choose to do, and probably just didn't think of when they were designing the API, and now have to patch with like a long and annoying URL. When I was at Dropbox, this was one of the bugs I found. So like, pretty normal. In a big application, it can become more complicated. You might have multiple domains that you want to handle. Like at Dropbox, we still own the getdropbox.com URL as long as domain name, as well as the Dropbox.com domain name. So like there, the checks were a little more complicated. But yeah. Yeah, why doesn't Django make this easier? I don't know. I think they just didn't think of it. They should have. Okay. So we've covered 3 classic attacks. I want to use these last, couple of minutes to talk to you about one more thing I want you to be aware of when it comes to security. As you've seen, there's a lot of creative ways in which people try to attack applications out there. We covered 3 very classic vulnerabilities, examples of which are being compromises, vulnerabilities that are leading to compromises more or less every single day. However, there's a whole lot of vulnerabilities out there. I don't want you to get the sense that you can memorize these 3 vulnerabilities and then your application is secure. The attacker has agency. They're always thinking, always coming up with new ways to attack your application. What makes them do this? Possibly they're just evil people, okay? Possibly this is how they make their money. They're an organized criminal. Possibly they're being paid good money by the governments of, I don't know, North Korea or Russia or something to do this, right? Or the US, we do this too, right? So the attacker is always thinking, always trying to find new vulnerabilities in your application So if you actually want to develop secure websites, you too always have to be learning more about what's kind of the latest going on. So, even classes of vulnerabilities are invented every now and then each of these classes have all sorts of interesting and funky ways that they can be applied. PDF injection, not super common, but if you're generating PDFs, which is reasonably common, it's something you gotta think. So if you're interested in security, or even if you're just developing web applications, something that you ought to be aware of is how to find out kind of the latest of what's happening in terms of vulnerabilities. Now, I'll leave most of that to Stefan in the security class, who apparently is doing a phenomenal job. He's a great guy. I haven't sat in his class, but I'm confident he's teaching you the right stuff. But I just want to give you two really short versions of this, two organizations I want you to be aware of. First is the CVE database, Common Vulnerabilities and Exposures. It is run by the US government, and it is a database of every security bug anyone has found in any application and reported. The criminals don't report here. So this is a trailing indicator at best. Nonetheless, anytime a bug is found that has security implications, it's good practice to report it to the CVE database. So here, for example, is one from this year. They get assigned a unique number. This one's called CVE 2024-9987. And from that number, you can tell this is in order. About 10,000 of these get submitted per year. So like lots of security bugs being found all the time. Naturally, if it's the same bug, you won't get assigned a new number. And you can look up this database by just going to cve.org. And we can just type that in here, 2024-9987. Hit enter. And here we have, a new vulnerability. This is a SQL injection in a CSV module for data collection in something called the Pandora FMS. I do not know what Pandora FMS is or even what FMS stands for, but someone much like you wrote that web application and they added a SQL injection vulnerability to it. And you can see information about it. The reason this database exists is so that administrators who are maybe running Pandora FMS can look up what vulnerabilities can affect their applications, stay on top of new bugs that are found, and know what risks they're open to. I'm pretty close to the end of class, so I'm just going to take your questions afterward. Sorry. So this is one thing. You can find these online. Here's the URL. What I want you to know is what a CVE is. It is a database of security vulnerabilities people have found and publicly reported. And by the way, you'll often see reported such and such bug has CVE number, and then it gives the ID. That's so administrators can look up for it. The other thing I want you to be familiar with is the OWASP organization, the Open Worldwide Application Security Fund. You can find it predictably at owasp.org. It is a pretty funky looking website, like pretty sketch, I would say. But one of the things they do is they keep a list of OWASP top 10. They do this by surveying application administrators and developers and looking through CVE databases. I'll take the comment now, sorry. And what they try to do is they try to make a list of what are the most common vulnerabilities that are seen in applications. So for example, you can see number 3 right there is injection. And for each of these, you can actually click in to learn more. So for example, here they have some information about how often injection attacks occur. They have some description of what these vulnerabilities are, as well as how to prevent against it. So hey, here's preferred option for preventing against injection number 1. It's use a safe API instead of generating code directly, which is exactly what Django provides for you. And then they suggest escape special characters using the specific escape syntax for that interpreter, as well as maybe don't let users type special characters. That's asking for trouble and maybe not hurting too many users. So once again, this is an organization whose goal is broader concepts of vulnerabilities that are common. They revise these, I think, every 4 or 5 years. I don't know if they have a regular schedule. And it's worth reading the list of vulnerabilities just to get a sense, first of all, of what mistakes you will make in your applications and how you'll get hacked by it. And secondly, getting a sense of which vulnerabilities are increasing and decreasing in commonality. One thing that's been really great is that injection vulnerabilities have moved down from number 1 to number 3 over the last couple of decades, I think over the last decade. And that is a big success by people in the software engineering field trying to make those more rare. You do not need to memorize the list of top 10 vulnerabilities, but I may ask you on the final what OWASP is and what it does. So like, what the OWASP top 10 are, and you'd have to answer something like, it's a list of common web application vulnerabilities. All right, so folks, that's all that I have for you today. On Wednesday, we will be talking about online crime. So if you want to prevent online criminals, I'll see you on Wednesday. I cut you off.